Well, I think we can start. Welcome back, everyone. So for today's class, we're finishing off section 3.6, and we'll probably make a start on section 3.7. And it's just going to be these two sections this week. So assignment number 6 is now fully posted. It looks like it's completely unbalanced. Like 3.6 is just going to murder us on all the problems, but those go quick. And 3.7 is our first, mostly just an application section. These ones take a little bit longer. So I feel like it's pretty balanced for most folks between the two sets here. Well, also that's new on the Moodle site is we have our second exam that's upcoming. And the information for the coverage is now posted, as well as the review problems as well. It's going to go from sections 3.1 all the way to 3.7, which is what we're finishing up on the end of this week here. Well, any questions, folks, with any of those announcements? Yeah, go ahead. It's going to be on, let's take a look. I'm really not sure, honestly. Monday, October 9. So still a ways to go. Other questions so far? Okay. Well, let's take a look at where we left off on section 3.6. There's two major objectives in this section. The first one is knowing how to take the derivative of any logarithm and also the specialized one, the natural logarithm of a. If you have those two down, then that's really the first half of these notes. Then the next thing we want to do is not just look at the natural log, which is inverse to the exponential, but look at other inverse functions. And so we found the derivative of cosine inverse, which, you know, that's a really tricky one, but we got through it at the last part of Wednesday's class. And I was thinking to start us off, how about we do one more like this, say y equals tangent inverse. Any questions before we try that out? Okay, let's make that our second problem of the day, kind of a warm-up. Turns out that one's a little bit easier than this, so it'll probably be a friendlier warm-up. Might help make this one a little bit more readable as well. So I'll put it down below right here. Let's call it a derivation since that's what we're really doing. And will be to find the derivative of y equals tangent inverse of x. So that's our objective here. And really all this is an application of implicit differentiation. It's good to know that there's some value to that stuff because that's a strange technique on its own. First thing we do is, well, I'll write down the equation first to start out, y equals tangent inverse x. Then the first thing we must do is take tangent of both sides, We want to wipe out that tangent inverse there because that's the unknown. We don't know how to differentiate it. But if you go like this, tangent y on the left, then you're forced to take tangent of tangent inverse of x on the right-hand side. And that's our nice cancellation. A function with its inverse, no matter which order we compose, as long as the variable is in the domain, it's just x, so no worries. You always get a cancellation in that way. So now we have tangent y is equal to x. Right at this stage, we're going to start by differentiating this implicitly. So I'll write down another line that goes, take tangent y. I'll go with a prime this time. You can use d by dx instead if you'd like to write out the derivative. On the right-hand side, it'll be an x prime as well. And now we just need to calculate these derivatives. So because it's implicit differentiation, it's good to be careful with the one on the left. And the reminder is that's really just a chain rule. It just doesn't look like that. But the more you eyeball it, the more it really feels like the chain rule. The tangent function is the outer function we'll handle first. And y, that's another function of x. In fact, it's right up here. We happen to know what it is. We just don't know how to differentiate it. So that one's going to be the inner function. So now when we go to calculate this derivative, here's what happens. First, it's derivative of tangent. Anyone recall how that one goes? Good call. We get a secant squared right away. Then we multiply by the derivative of the input because we don't have just x there. So right inside here, we'll put in a y. And a y will go right there as well. So there it is. That's our derivative. It's being called y prime at the moment. You could call it dy dx on the next step if you like. And on the right-hand side, we're just taking derivative of x. That's a nice one. It turns into a 1. So we're almost done with the implicit differentiation. You know, what the heck? Let's leave this one as a y prime. It's completely valid. And we can say y prime equals 1 over secant squared of y. We truly have a derivative, but it's not the one we really want. Even though I'm not using Leibniz notation to say dy dx, there's still a requirement that your function came in as a variable x for its independent variable. Your derivative must have the variable x as well. So this is where we have to do something to try to bring it back. Well, we're dealing with trigonometric functions, so sometimes if we're not sure where to start, just write down identities. So here's a list of helpful identities, starting with probably the most important one, cosine squared of theta plus sine squared of theta equals 1. That doesn't get us anywhere, so we go to the next big identity. This one goes tangent squared of theta plus 1 equals secant squared theta. And that's more relevant to us because we have a secant squared y. We can swap that out with a tangent squared plus 1 if we so choose. Well, first let's write down one more identity because these really come as a triple. For this identity, if you change tangent to cotangent and change secant to cosecant, you have the same exact identity. Well, not the same exact identity. You have a new identity that's also true. So cosecant squared theta. We'll use this one right here. So the secant squared y, we can make it become 1 plus tangent squared theta. So that'll be our next step. So y prime is now 1 over. I'll go 1 plus tangent squared theta. It looks kind of funky to make tangent squared theta come last, but it's only for the formatting of how the book ultimately ends up writing down their answer on this one. Oh, and I did make a mistake. Sorry about that, folks. I put tangent squared theta. I was looking at that a little bit too closely. Instead of theta, what should it really be? Exactly, it should have been the original independent variable y from over here. Let's put that correct value in. 1 plus tangent squared y. Now, well, that didn't help, did it? We used an identity, we got to here, but we still need the variable x. Anyone see what we could do next to bring it back? You're saying over here? Or this one up here? Yeah, that ought to do the job for us. If we were to put that in, or even this one down below, here's what's going to happen. I'll use your approach right here with the tangent inverse. You can throw that in right here and say tangent squared y is now, I'm going to bring the exponent into a more natural looking position. Tangent y squared just is a little bit more readable for our substitution, which turns into tangent. Now we make this substitution right here. Y becomes tangent inverse. Still to the power of 2. But just like before, there's a cancellation immediately. So we now have x squared It's a weird way to write it, but it's just showing that there's a cancellation on the inside here, leaving just x. So normally we would just write that as x squared. So we got it, folks. We can substitute out that value for y coming up from here or from down here, get a cancellation, and it turns into 1 over 1 plus x squared. So really bizarre function. We know that if we differentiate any of the 6 trig functions, we get other combinations of trig functions back. Derivative of cotangent is cosecant squared negative, for example. But if you take the derivative of an inverse function, an inverse trig function, you never get an inverse trig function back. You get these weird algebraic forms that come back. Very kind of odd. We did it, folks. That's our second derivative to run through. There's 4 others, but we'll leave it to the author to show us what those ought to look like. Any questions or comments at all getting through this derivation here? Okay, well, let's take a look at the full set of formulas then. And there is quite a lot, but the more you practice using these, the more you say work on memorizing them, the easier they get to absorb. So here's our second table. The derivatives of the trigonometric functions are supplied down here. And now if we go to the inverses, here's what the inverses look like. We calculated this one down below right here, 1 over 1 plus x squared. And just by the way, something to mention about these documents, this happens on PDFs as well. If something just doesn't look right, like that x there, it's probably a zoom factor. Just change how you're zooming and it should resolute better. This happens a lot on phones, like you're doing a homework assignment. A negative might not show up on your PDF, depending on how you're zoomed in onto that thing. But there they all are. They don't exist in isolation. They do have some patterns that we can conflate with the original derivatives of trigonometric functions. So let's study both tables at once just to see what are the patterns. The first big pattern is if you always go sine, cosine, tangent, and then the reciprocals in the same order, then you'll see negatives showing up in these locations. But maybe a better way to say it is when you took a derivative of a co-function, there's always a negative that shows up. Down here, if you take the derivative of an inverse co-function, that's quite helpful. You still get negatives showing up. So that's really nice. And there's other pretty interesting patterns. Notice that if you memorize this one, you have essentially memorized cosine. That's pretty much the strategy I try to use memorizing this table, which is nasty. Lots of flashcards got used up for this. But if you know sine inverse, it's the same for cosine inverse. You just throw in that negative sign. Likewise, if you know the derivative for tangent inverse, you have the derivative for cotangent inverse. It's a co-function, throw in the negative sign, and you're in business. And last one, memorize the derivative for secant inverse. This one is really bizarre. 1 over x times the root of x squared minus 1. And you have cosecant inverse. Just throws in that negative sign right there. Well, you have it, folks. That's our full table. Yeah.
We got a question like this on the exam. We didn't write our entire work, we just put in the answer.
You're saying if a question says differentiate like the tangent inverse, put in 1 over 1 plus x squared.
Yeah.
Exactly. Yeah. This was more just practice on how you get there. And it was also reviewing implicit differentiation, but you would never have to do it this way. I would have to say derive it specifically. Otherwise, you'd use the formulas. Other questions at the moment? Okay. Well, we've got our trigonometric functions down. And one thing that is pretty noteworthy about all of these is my exams are open notes. So this is good stuff to put on the exams. I absolutely would recommend that. It's horrible to feel like you've got it down pat and just forget. But I would encourage you to memorize these regardless. And there's some certain reasons for these. Let's put a note right here. It's important to memorize both tables. The importance could be stated if you go to take a derivative or if you go to integrate something. If you have to look up any one of these 12 different values, you're just taking a lot of extra time. If you see a cosine come up and you know you have to differentiate it, you know from muscle memory, it's just going to be negative sine x. You're going to be much faster in your computations It just means you're going to study a lot more and do a lot more with your time once this is memorized. But there's a second reason for this. If you're taking a class like Calculus 2, Calculus 3, or even beyond, knowing what these are could be a lifesaver. For example, one problem in Calc 1 or in Calc 2 could go like this. This looks a little bit bizarre, so we'll explain it and mention we're getting to it, but we haven't done this kind of thing before. But one problem goes like this. We put down an elongated S. It's going to be referred to as an integral sign or an antiderivative. Put in something familiar, like say 1 over 1 plus x squared dx. And that could be one entire question in Calc 2. But if we are not familiar with how 1 over 1 plus x squared is tied in with tangent inverse, we might not know just what to do with that. This turns into the left-hand side. Tangent inverse of x plus an arbitrary constant. But this is the value of the table. The table actually goes two ways. If you go this way, you're differentiating. Derivative of sine becomes cosine. If you're going this way, you're finding an antiderivative, or integrating, some people might say. You're taking what was an answer, and that became the question, and that right here, tangent inverse, is the answer here. So this is not as easy as a table as it looks like, and we'll have more derivatives. The more you internalize this, the more you memorize it, the much easier it's going to be to deal with this portion right here once we start integrating. Let's say here, this is for integration. So that was my small spiel on this table. It's honestly kind of sucks to memorize all this kind of information. It's just brute force memorization. But the more you work on that, the easier this kind of stuff goes, especially if you're going further to more and more calculus topics. Well, any last questions or observations that folks see on this table? Okay, well, let's practice taking these derivatives next. And that's what we're going to end the notes here on for this section 3.6. We're just going to differentiate stuff with the whole purpose of just becoming more familiar with this table here. Let's call this one a part A. And part A will go f of x is equal to tangent inverse of the natural log of x. So that's our problem we'd like to calculate. Right out of the way, would you call this a product rule or a chain rule? Good call. This one's absolutely a chain rule. For it to be a product rule, it would have had to have been tangent inverse of x as well, times the natural log x. Here, natural log is going inside tangent inverse, and so we'll analyze it this way instead. I'll call this 1 for the outer function, 2 for the inner function, just the order that we're going to differentiate them. Now for the derivative, f prime of x, we need first the derivative of the tangent function. Good news is it's right here on our page, so we don't have to look too far wide. I'll first put down that derivative. It goes 1 over 1 plus a quantity squared. Then we multiply by the derivative of whatever that quantity was. Finally, take the inner function, natural log x. It'll go down here and right over here. So that went through the chain rule portion. Right here, that's the derivative of tangent inverse. Now we just need to differentiate the natural log of x. Good call. We get just 1 over x there. So the whole thing becomes 1 over, I'll put parentheses around 1 plus natural log x squared. Right where the black or red dot is, we get a 1 over x. And so we could just put it back into that denominator if you like. So finally, that's our full derivative. Nothing much happens with it. Pretty much none of these are really going to simplify in a huge way, at least not in the homework. I do have one in the notes. But any questions, folks, on getting through this one? Okay, it's at least not a new differentiation rule like chain rule, product rule, quotient rule. It's just a new table of derivatives. So if we're familiar with those kinds of rules, product rule, quotient rule, and chain rule, it's not so bad, just new information we have to pull in. And let's try this again. So for part B, let's see, let's let this one be g of x equals sine inverse x times cotangent x. Now this time it's got to be the product rule. Would folks agree with that so far? Awesome. Also, this one's really kind of nasty in a way. When you see sine inverse right here, it means you're using that as a derivative from this table. But if you see a cotangent, definitely don't use this one. That's not a cotangent inverse. We have to use the prior table and get negative cosecant squared instead. So the thing to definitely watch out for is the homework set and on exams, watch out if they get mixed, the inverse with the non-inverse functions. So this one is going to go g prime at x to start equals, now depending on how you feel about the product rule, you could calculate in this way. I'm going to take the derivative of the first factor just right here and now. Derivative of sine inverse x, we can refer to the table above, becomes 1 divided by the square root of 1 minus x squared. So I've differentiated sine inverse, and the product rule says multiply that by cotangent x. So I'll go times cotangent x. Then there's a plus in the product rule, so plus comes in. On this step, we have to copy the opposite function. So I'll copy sine inverse. Then differentiate the cotangent function. I'll go here times negative cosecant squared x, or derivative of cotangent. Then we did it, folks. That's our product rule in action. Does that make sense to everyone visualizing it this way? Awesome. So now that we have that, you know, if you left it like this, I wouldn't be too worried about that. But I think it does kind of simplify, but it's more stylistic this time. It's easier reading to call this over here a cotangent x divided by root 1 minus x squared. And over here, it's much easier to read and understand if we just call it minus cosecant squared x sine inverse x. If that was an ordinary sine x, we could actually simplify this, but it's not. That's an inverse function. They just land right as they are seen right here. Well, that's two derivatives so far. Does these make sense so far, folks, getting through them? Awesome, glad to hear that. Well, let's try out another one along these lines. Let's make this our part C coming up next. And part C is just a function labeled as y. So we're not using function notation, but it's still a function. Y equals cosecant inverse of secant theta. So this one is now getting a little bit nastier, but if it was an exam problem and you differentiated normally, but didn't take loads of steps simplifying, that would be okay. This is one of those problems where the back of the book goes through extreme efforts to simplify a whole bunch. But I want to mention as we solve this, there are points you can stop. You don't have to take loads and loads of algebraic steps. Well, the first thing we have to do is identify the rule on this one. Secant is going inside cosecant inverse, so we have to hit it with the chain rule this time. So as per chain rule, this one's the outer function we'll deal with first. And that will be the inner function we'll deal with second. Next thing we need to do is put down the derivative for cosecant inverse. That one's tricky. We didn't derive it, and it's in the table above. It goes dy dx. But first thing you can say, it's a cofunction, so there's a negative sign. Automatically, that would be partial credit as an exam problem because that's knowledge that you get a negative when you differentiate a cofunction. Then in the numerator, there's a 1. Down below, there's a placeholder here, root, placeholder squared, minus 1. Let me put just a quick note. D dx of cosecant inverse x is 1 over x root x squared minus 1. So when I went to differentiate this, all I did is put down this as a template where there's parentheses in place of x, where x was. To me, this is a harder use of a chain rule because there is two spots x occurs. Then the chain rule is finalized once we multiply by the derivative of whatever that output happened to be. So now there's three spots. We're going to put the same function in all three. Anyone see what the function would be? Exactly, secant theta goes right in all those locations. So that's the inner function 2 now in action. Secant theta here, here, and here. When we put a 2 here, it means we're differentiating secant theta last, and there it is. That's our last derivative to take. Well, any questions, folks, to this stage? Okay, we still have to crank out this last derivative. It's going to go like this. There's a negative here. Down below, we have secant theta, square root of secant squared theta minus 1. And derivative of secant theta. Anyone recall how that one goes? Awesome, you folks are getting great at this. It's a secant theta tangent theta, as you said. So we did it, folks. That's our whole derivative. Now, the simplification on this, there is one thing we ought to do no matter what for a problem like this one. Anyone see the required simplification? Yeah, we ought to cancel those immediately. I mean, it's tempting not to, right? It's going to reduce the derivative format by quite a lot. Now we have negative tangent theta. Divide by the root of secant squared theta minus 1. Here's where you could stop if you wanted to, but do you see another thing to do on this one? Yeah, absolutely. I don't think we have to multiply the root as much, but we could just put tangent squared right there and then take the square root. Absolutely. So our identity was, let's put it over here on the paper. Tangent squared theta plus 1 is secant squared theta. We wrote that above on the earlier problem. So good eye, you see a secant squared, you can probably work with that. Subtract 1 from both sides, and tangent squared theta is our secant squared theta minus 1. And we could put that in right here. A tangent squared theta goes in that location. Does that make sense at the moment? Awesome. I just want to point out though, if you ever feel like you're doing calculus, but your answer is not matching up in the back of the book until you take like a dozen algebraic steps like we're doing, it's okay to stop here. So I want to just emphasize that this is acceptable as an answer. But let's keep on going just for the sake of practicing trigonometry. I mean, that's what we're doing right now. It's essentially trigonometry. On the next level, we get negative tangent theta square root tangent squared theta. And this is where it gets even weirder. I always have this big temptation, me personally. If I square root something squared, I'm just going to put a tangent down below. That means it'd be negative tangent divided by tangent, and the whole thing should be negative 1. But there's a mistake buried in there somewhere. Anyone happen to know what it would be? Maybe let's take a look at Desmos just to start us off, to get a feel for this. Need to find the home row first. There we go. So if we put this answer into the calculator, here's how it comes in as negative tangent. Can we put a theta? I guess we can. Well, we have a theta now. That's fancy. Square root secant. I don't know if we could put a power 2. Hey, it works. Theta goes in there, minus 1. We want this to be something I'll plot, so I'll just call it y equals. So there's our graph so far. These vertical segments are not quite right. There should be no vertical segment there. That would fail the vertical line test immediately, but that really is a true function. So there's some anomalies on here. Ignore the vertical segments, but these dash segments are actually accurate. So now if we took the square root of tangent squared down below, I got a tangent, cancel with the tangent above, we would have been looking at this graph instead, just a negative 1. But it's far, far weirder than that. So let's see what's going on algebraically down here and see if we can simplify it further. So the missing thing that is making our algebra weird is that if you take a square root of anything squared, I'll just call it x squared in the notes, it's not x truly. Anyone know what it really should be? Exactly, there's two possible versions. It's either positive if x was positive or negative x if x was negative. So you could write that in as absolute value of x altogether. That's kind of an unfortunate fact, right? When you reduce a root like this, the only times you're allowed to eliminate the absolute value is if you know your function could never be negative. Oh, I see, that's kind of awesome. So now we're going to put this over here and say, this is negative tangent theta, divide by the absolute value of tangent theta, and it doesn't simplify from then on at all. That's our actual function. Let's plot that one and see how close we got. So I'm going to eliminate this, call it negative tangent theta divided by tangent theta in absolute value. Somehow, some way, the graph is more correct. It doesn't have vertical segments. The square root must have been just messing up Desmos somehow. But this is the real graph for that as a derivative. A very bizarre, awful looking function. And even if we put this in, which we did, it's the same graph. It just looked like it had anomalies on our last try. Well, we did it, folks. That's our derivative of this function. And they don't really get too much worse than this. I think there might be one that simplifies, but go for the low-hanging fruit, easy cancellations, combining like terms. Those are the major things I'm going for really all of these sections. Well, any last questions, folks, on any one of these derivatives? Okay, well, we are starting to get to a certain point in this course, once we finish section 3.6, where we have a huge catalog of derivatives we could take. They could be power functions, polynomials, square root functions. Now we have the trig functions, their inverses, and same with the exponentials and their inverses. We'll see more in section 311 when we go to hyperbolic functions. But for the moment, we're going to pause for just 3 quick sections and do a few applications. So that's where we're going to start off next in section 3.7. Let me just move this over. So now we're in section 3.7. The homework is, again, just these 3 problems here, but they're tricky and longer problems, so they're going to be worth 15 points each. Let me actually grab those notes. And I wrote these problems here to help support us with those actual problems, but always a standing offer. If you're stuck on any one of those, don't hesitate to ask. I'm always happy to help out. Here, to start us off, is just a reminder of some information we saw in section 3.8. Let's run through this. In 2.8, we defined a position function. That's going to be the position of some object. It could be a particle or a person. And we're only tracking one dimension, displacement from a starting position. So the person is either moving up or down in one dimension or left or right and so on. If we differentiate the position function, then we obtain the velocity function via t. And we can write it this way. In prime notation, it's the derivative of s, so we put an s prime on it. Or in Leibniz, we can call it ds dt. Then we can keep on differentiating this thing. On our next derivative, we could get acceleration. And acceleration, same as before, we could write it out this way. It's the first derivative of the velocity function or the second derivative of position. If we wrote it in Leibniz notation, there's 2 options for this as well, either dv dt, that's taking the derivative of velocity, or d2s dt2, that's the second derivative of s coming up above. So with that information, that's what we're going to be looking at. We have an object moving in exactly one dimension. We want to look at the motion of that object. Any questions first with these notes here? Okay, so here's our example. It says a mass on a spring vibrates horizontally on a smooth and level surface. So when we say smooth level surface, it means the model that we are putting to this moving mass right here is not a perfect one. We're assuming that there's no friction whatsoever, that the only resistance that X ever experiences is coming from the actual spring itself on this diagram. So when it says the mass, that's this thing right here, that entire block. My arrow looks weird. The spring is this thing. It's extending and contracting with time. And the motion really looks weird, right? It's a variable x, but it's a function of another variable, time. We'll see this quite a lot in the upcoming section on related rates in 3.9. And so essentially what this is saying is x is going to be the displacement in centimeters. So here's the centimeters. As time changes, this x right here is just your position away from zero. Sometimes it's on the negative end, sometimes on the positive end. But that's its equation of motion right away. And so part A says, calculate to dx dt. It makes sense that we should write our function as x of t because it's just x which is changing and its position depends on t. But it definitely looks weird. Any questions at all, folks, with that function or the diagram? Okay, part A says, we're going to calculate dx dt, evaluate it when t is 2 pi over 3, and then give a practical interpretation. Let's see if we can fit that in just a little bit better. So first thing to do is we'll go to x here. You could call this an x prime of t if you prefer. So that's always valid. But if your variables just look strange, if x is suddenly not just a variable, but a function of a different variable, Leibniz notation is designed to help us navigate through that. So I encourage you, use Leibniz in this weird context. So I'll go dx dt, the derivative of a horizontal position x with respect to time. Go back to the function, and that's just an ordinary derivative. H is a constant multiplying, so it copies in. Derivative of sine goes to cosine. So it just becomes 8 cosine t. Honestly, the hardest thing about this derivative is the x of t right there. It's just weird, so it gives us a little bit of mental noise we have to run through before we do the normal thing of getting 8 cosine t. Next thing we need to do is we're going to evaluate that when t is 2 pi over 3. So the next work will look like this. Dx dt, when t equals 2 pi over 3, is going to be equal to 8 cosine 2 pi divided by 3. Now, at this stage, we have to calculate that. But on your exams, you'll always have a trig table, so that's going to be helpful. The trig table will look essentially like this. There's a pi over 3 that comes over here. It's not the one we want, but 2 pi over 3 is in this quadrant. When it's asking for the cosine value, it means the coordinate we want is going to be the first coordinate. And even on a shoddy drawing like this, you can practically guess that x coordinate. It looks like -1/2, and that turns out to be the exact value. On the trig wheel that you'll see on the exam, you would just grab that -1/2 value from the coordinate it gives us right here. So this turns into 8 times -1/2, which gives us a -4. But that -4, it is kind of special, actually. It's a velocity. We took the derivative of a position function, that's what x was, measuring the position at time. So we have a velocity of -4. The units will be, well, first, the unit of the numerator. The unit of x was centimeters, so -4 centimeters. Per, the unit in the denominator, that one was time measured in seconds. So I'll write centimeters per second. The per I just wrote as a fraction bar. So that's the velocity of the object at time is 2 pi over 3. Any questions, folks, with that so far? Okay, well, we did a derivative, we evaluated it, and oftentimes, I would say this is the hardest part of the entire problem. We're still just kind of practicing interpreting derivatives, but they become a bigger and bigger deal as we go to section 3.8 and 3.9, and culminating in chapter 4, we'll do a lot of this kind of work as well. Here's what an interpretation might look like for this. We can say at time t equals 2 pi over 3 seconds. So we need to mention the exact time in question when it comes to these kind of derivatives. It's about what's happening to the mass. We have a velocity of -4 centimeters per second. And what that means is the mass is moving to the left. The left is what's carrying that or capturing the negative in that derivative right there. If it was a positive, we would have said it's going to the right. But at 2 pi over 3, it's heading off in that direction, leftwards, at a rate of 4 centimeters per second. If we put 2 pi over 3 inside this right here, let's do it just for the sake of explanation. X at 2 pi over 3 would be 8 sine 2 pi over 3. Looking up the value for 2 pi over 3 on sine, it's really close to 0.9, and that's the root 3 over 2 value. So it becomes 8 times root 3 over 2. So 4 root 3. And this would be 4 root 3 centimeters to the right of the 0. So somewhere out here. So at 2 pi over 3 seconds, this is just where it ends up, 4 root 3. So somewhere over here. But at 2 pi over 3 seconds, the velocity is -4 centimeters per second. That means it's moving to the left at that rate, 4 centimeters per second, but only at that one instant of time. Change the time to something else, it might be moving to the right or still to the left, but at a different rate. So this is just a snapshot of essentially what you might see on a speedometer if there was such a thing on this thing right here, like in your car. Well, any questions at all, folks, on getting through this one?
This equation would be assuming that it's not moving.
Yeah, exactly. So it's kind of a silly example that as a model, it might be accurate for a few minutes and then it becomes completely nonsense after a while. So a super, super idealized case with those assumptions there. Other questions or comments so far? Okay, well, that was our first derivative in the problem. It wants us to do it again, calculate the second derivative. Well, if we differentiate once and we got velocity, then differentiate second, now we're dealing with the acceleration in the problem. So I'll code this in blue just as a reminder. This is now an acceleration problem. Our first derivative is right here by the red dot, so it's really not too bad. We're just differentiating again. So we'll say d2x, meaning the second derivative of the position function x, dt2, meaning we're using the variable t both times, it's the only variable. We take the derivative of 8 cosine t. First constant multiple rule says copy in the 8 because it's multiplying. And derivative of cosine t turns into a negative sine t. So if you like a better format, it became -8 sine t. And now the next thing is to evaluate at 2 pi over 3 seconds. But first, does that look all right to folks on that computation? Awesome, let's go off to the next part. Second derivative with respect to t, evaluated now at t equals 2 pi over 3 seconds, will turn into this. I think I need a little bit more space. Let me go down. All we're doing is plugging 2 pi over 3 inside that derivative that we just calculated. So now it's -8 sine 2 pi over 3. We've evaluated sine 2 pi over 3. It's right up here. Turns into a root 3 over 2 if you check the trig wheel. So -8 times root 3 divided by 2 gives us -4 root 3. And we're going to interpret this one as well. And any interpretation, you can put a unit on it. It sometimes does help. Anyone happen to know what the units should be for this one? Good call. The unit is still centimeters in the numerator, but we're talking about the rate of change of velocity with respect to seconds. So it would be centimeters per second in another denominator. Easiest to just call it centimeters per second squared, as you called it. So that's our unit on this one. So this is the rate of change of velocity. It's still moving to the left at 2 pi over 3, but the rate at which it's moving to the left is decreasing by this amount right here. So we can say next, the rate at which the mass is moving to the left. I said decreasing, I misspoke on that. We ought to say is increasing by 4√3 centimeters per second squared. I honestly think that this second interpretation is really kind of tricky. And one way to see this is, once again, through Desmos. Let's take another look at what's just happening here. The equation of motion was, forgot, 8 sine t. Okay, let me go back down here. So I just want to plot right away. Let's call this x of t equals 8 sine t. Oh, they're trying to graph something else. I shouldn't use an x variable. I'm just going to use a generic y equals 8 sine t. That's the function I was expecting here. We should say that time starts at 0. Let's go to something like 2 pi. That ought to be just fine. So here's our graph right here. At 2 pi over 3, we would be about right here. Let's double check that. 2 pi over 3 is about 2.09. Okay, I think we have a good picture now. 2.09 is about right here. So roughly at that location. So when we said it's moving to the left, we meant it was going down towards 0. Recall our scale, it went horizontally. So imagine that that whole thing just got flipped up to match what's happening here, measuring the height at any time. So now when we're at, oh, I'm losing my place, sorry, 2 pi over 3 seconds, there we go. We're right around this location. The mass is moving downwards, but the rate at which it's moving downwards is actually increasing as well. It gets faster and faster until it gets to right around here, the inflection point. Then the rate at which it's moving down is slowing. It's starting to level off. It gets at its slowest once it gets to here. Now velocity is positive and acceleration would be positive as well. So the fact that we got a negative sign right here, and the fact that the first derivative, velocity, is also negative, if velocity and acceleration have the same sign, you are now moving even faster in that same direction towards the left. This one was a little bit trickier than it had to be, but I would say if you're happy with -4, meaning moving to the left, that's the bigger takeaway on this one. Let's add this to the notes just so that there's a paper trail. If the velocity and acceleration have the same sign, then the object is increasing in speed. So that was what's happening in this particular problem for our mass. Does that make sense to folks on this particular situation here? Okay, let me take another look at our explanation or interpretation. The rate at which the mass is moving to the left is increasing by 4√3 centimeters per second. I did omit one thing. When time is 2 pi over 3 seconds. So that's what's happening on this interpretation here. Well, kind of a tricky problem, but any questions or comments about it? Okay, these are the kinds of questions that we're getting into in this section. And they are a little bit messy. Some of the derivatives are a little bit tougher to get through. Some of them are tricky because just the interpretation is what's tricky. But let's take a look at what we're getting in next. Let's see, we have a good 19-ish minutes. Just to make sure we don't break a problem in half from Wednesday to Thursday, I think it might be a good idea to skip example 2. That one's a little bit long. So let's go to example 3, since I think we can finish this one in a reasonable amount of time, make it our last problem. Is that all right with everyone today? Awesome. That way, it's always kind of is awful to do a problem and then sit on it for 24 hours before we finish it. So this is one we can absolutely tackle and finish off. It's a really fast situation. It says a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. We want to calculate dAdt at t equals 4 and interpret its meaning. So this one's weird because it didn't give us much information. I would say the big strategy for this kind of problem is try to draw something. I mean, even in the first example we did, there was a drawing of the mass moving on the spring. So anything you can draw, I mean, at least it's allowing your subconscious to work on the problem. You're thinking while you're doing something else. So that would be my stone. It's dropped into the lake. It's creating a circular ripple. So here's my circular ripple, nothing fancy. More artistic might be nice, but you don't want to get too carried away. It says it's traveling outward at a speed of 60 centimeters per second. So for that bit of information, I'll put a line that comes out like this, maybe an arrow just to signify it's changing, and say that that's arrow is increasing in length at a rate of 60 centimeters per second. So we have something down here. Next portion of the problem says, calculate dAdt. That's kind of a rude problem because they never even told us what A was. But A, well, it ought to be the area of this entire wave that's propagating from the dropped stone. I think that's what makes the most sense. So first thing we should do then is put down a formula. A, the area of that ripple will be pi radius squared. So we have an area. You need to differentiate that area. But the derivative I would like to take would have been dA dr. That's the derivative that makes sense, right? Because for this area formula, it's a function of radius. That's not at all what they asked. They're asking for dA dt. So that's what makes this problem a little bit kind of confusing in a certain sense. We go back to the drawing board and decide, well, if there's a time component, where should time actually go? Anyone see where it ought to be? Exactly. So this right here is a wave that's propagating at 60 centimeters per second, but it's also what goes in place of r squared, like you said. It's literally the radius. So I'll put a little arrow here to say, this is r of t. And you said the function should be 60 times t. Absolutely, at 1 second, this would be 60 centimeters away. At 2 seconds, well, it's going 60 centimeters per second. This would be 120 centimeters in length. So this would be our function right here. If your speed is just a constant, your function would look like this, the constant times time. Does that make sense to folks on putting in the radius portion? Awesome. To me, that's the most confusing thing about this. But now, if you know that there's a 60t coming into play, we can put that inside here and just work with it. Now there's a couple strategies, but you mentioned put 60t right inside here. So let's do exactly that. A is now going to be pi. Throw in 60t squared. With the approach we're taking, we're just saying exactly what the area function is and simplifying it as much as possible. So next thing we can do is, well, let's just square that out. This will be pi. 6 squared is 36, and then we'll get 2 additional zeros from that. And then t squared. So finally, area is 3600 pi times t squared. And finally, we can go back to dAdt, and we can calculate that thing because we wrote a as a function of time now. It's now an appropriate derivative. So we'll go back to this and first worry about dA dt. Any questions, folks, to that stage? Okay, next thing to do is differentiating this function, it's just an ordinary kind of derivative. 2 will come down when we take the derivative. And so now it's 2 times 3,600 times pi t to the power of 1. And if we simplify that, we have, let's see, we're getting 7,200 pi times t. Well, we have the derivative at any time t. This is the instantaneous rate of change of the area of that circular ripple with respect to time. What we want to know is, at what rate is the area increasing when time is equal to 4 seconds specifically? So here's our next step. dA dt, evaluate it when t equals 4 seconds, which just means we're plugging a 4 right inside here. So nothing too major. 7,200 times pi times 4. Now at this stage, I'd probably grab a calculator. I'll use Desmos because it's just available right here. Let's go 7,200 times 4. So if we want to answer in steps or using pi as well, it'll be 28,800 times pi. I'm happy with that answer. If you want a decimal approximation, you can multiply by pi right here now. I'm okay with that as an answer as well, giving us 90,477.9. Just round to what seems appropriate to match the problem. Let's go with this answer, the numerical value, 90,477.9. Now we need units in this thing, but the numerator is an area, and we were giving information in terms of centimeters. So this should be centimeters squared per, the denominator is t, which means we're dealing with time, so second. So we have the derivative evaluated at 4 seconds. We just need to say, what does that number actually mean? That's not the area of the ripple at 4 seconds. The area of the ripple at 4 seconds, well, that's just plugging 4 right here and squaring it. It's like the velocity, exactly. So it's not exactly a velocity problem, but that's the right thought. It's the rate at which this area increases right at the moment of time, 4 seconds after the drop of the stone. If it were 5 seconds after, the area is bigger and it's also increasing faster as well at that stage. So putting it into words, that's always a little bit challenging. Let's say at time 4 seconds, the area of the ripple is increasing at a rate of 90,477.9 centimeters squared per second. It would be expecting the sentence, yeah. And the components that I would be looking for is, we have to mention the time. We're using the context, so we have to mention area somewhere and give the value there. And those would be the major things I'm looking for. You could shorten it up a good deal. I wouldn't be too worried. But if it has those components, I consider that a great interpretation. So we did it, folks. That's the breakdown of this applied problem, getting an output and interpreting that output. How do folks feel about it? Does it make sense getting through this one, or does it feel like it's kind of challenging? To me, I feel like they're super challenging, especially this one right here. I would never give you this kind of problem as an exam problem. Exams are timed at 67 minutes. And when you see this, you're meant to just pause for a while, kind of go over it, think of ideas for around 15 minutes before you even get started. The big things were to know to put down the area formula. And this is even the bigger thing, to know you have a hidden function, the rate at which this segment gets bigger. Those are not things I expect you to just produce like that in an exam setting. So the exam questions are definitely much more directed. Well, any questions, folks, with getting through this one? Okay, and maybe just one last comment. This one's a good one for helping with the homework, as was with this one. But I would say doing example 1, either part, just the part A or just the part B, these are more similar to what you would see in an exam setting. Because all the work of making the function has already been done. And that's sometimes the most challenging part about these kinds of problems, devising the actual function like we did right here. Well, I think this is a good stopping point for us, folks. We're ending about 7 minutes and some change. But that's because my problem down below and my problem above, they're 25-minute problems at least, but we'll be sure to give these a try. And if you have any questions when we come back, don't hesitate to ask. I'll be happy to help out as well. Have a great day, folks, and we'll come back on Thursday. Yeah, go ahead. Sorry, say again. I would say not the third derivative. Yeah, probably not for this kind of section. It's something that'll come up more often in chapter 4. Oh, so if you're thinking maybe in terms of these things, first derivative is velocity, second derivative is acceleration, and the third derivative is something that is used in the real world. It goes like this. If you go, let's see, J of t equals S triple prime of t, then this is the, I don't know why they call it this, jerk function. So I believe the reason people are interested in the jerk function is, imagine you're an amusement park person, you're building a roller coaster. A good roller coaster should have a tame velocity. If you had a constant acceleration the whole way through on your roller coaster, people are probably going to die. And your jerk function should probably be 0. That's non-zero. It's going to be a wild, wild ride. So that's maybe one use of that. Other questions at the moment? Okay, thanks for that question there. That's a good question about that derivative. Again, it's something that people look at, but I think you'd have to be like in a physics or modeling class for it to be really hit on harder. Any questions?
Yeah, the 37. I don't have the same answer as the book, but I just want to make sure that it's right or I'm
Gotcha.
wrong.
Oh, so it was this one here.
Yeah.
Expand it out. And then here, expand it out, looks good. Then derivative goes 8x cubed. This one's nasty because this is the product rule. So
Right.
4x squared, then y squared, 4x squared, then y squared, that looks good. 8y cubed and dy dx. Okay, looks great on this line. And then here you have 8xy squared. You've got the dy here, that looks good. Now next we have to solve for the dy dx.
Okay.
It appears here, here, and here.
Mhm.
So what I would do with this one, I'd probably add the 50 y dy dx to this side.
Okay, so you just, okay, that's a good question. So with all the DYDX, you just move them over and then anything that doesn't goes over.
Goes to the other side, exactly.
Okay,
So I would subtract this portion, just those two goes up
Yeah.
to that side. This goes over here is a positive 50y.
okay.
Then factor up the dy dx on everything over here and
Mhm.
divide by the other part.
Okay,
Does that make sense for that one?
yeah,
Awesome.
sweet chicken.
I'm on the same problem, and I had everything right. Besides, I don't know if this is the right answer, or if I'm like factoring it out right, because I get 16 as my slope,
Oh,
and that
gotcha.
is not the right answer.
Let's take a look. So going through this one,
That's why I left it like that. I was like, oh.
this looks good. And then moving, yeah, you've got the 3 things here. So you have the 8xy should have came from,
Like,
8xy. I see where this
My
came from.
8xy is from the 4x.
Oh, gotcha. Good eye, couldn't see that one. So
Yeah.
8xy comes from there. That looks good. 8y cubed comes from here.
Mhm.
This was negative 50, turns into positive, so it came from here. 8xy, 8y cubed, so that looks good. The numerator should be negative. I think this one is the issue right here.
That one,
That should be a negative sign as well.
okay,
So it all looks absolutely correct. It's just the tiny things.
okay.
I have a few questions.
Sure.
Okay, so on this one, I don't know where to start there.
Oh, so it was like something like find the slope of the tangent line at that point?
Yeah, I think so. Yeah, that's what it was asking.
Gotcha. First thing you want to do is just differentiate your white line.
Okay, so then it's would that be one?
Mhm.
And then cosine.
Yeah, one and a cosine
And
x.
then cosine
Then
x.
after you have that, of pi inside, your one plus cosine x, and you would get the slope out.
Okay.
So it kind of looked like this. I forget I have a, what to draw on here. So your y prime is one plus cosine x. That means your slope m is going to be one plus cosine pi.
Okay.
Cosine pi is -1, so this will, looks like it comes out as a 0.
Mhm.
And then to get your full tangent line equation, go y minus y1 equals slope times x minus x1. Your x1 is the pi and your y1 is pi as well.
Okay. Okay, that makes sense.
Awesome.
And then. Sorry,
Oh, no worries.
number 16, so I got this far,
Yeah,
and so I don't know what to do after that.
let's see. So cotangent goes to negative cosecant, either t minus, then cotangent. And here you have e to the t prime,
Would it just be one,
but well, the derivative of e to the t will just turn it into itself, e to the t.
e to the t,
Yeah,
so,
so yeah, you can just erase that there, and now it's correct.
okay,
Then at this stage, you can cancel e to the t here, here, and it'll leave a power 1 of e to the t.
okay,
And I think that's pretty much all you can really do with it at that stage.
okay, cause I got stuck there, and I was like, I don't know what to do next.
Yeah, so if it cancels here and here, you can also put a line there
And
through
I
the
just have
exponent.
one down here,
It would just be the e to the t to power 1, or just e to the t.
okay. And I think that's it, for yeah. Okay, thank you.
Yeah, you betcha. Sorry, I kind of lost track of the order. Gotcha.
We actually had the same question. We're just wondering if we have solved this correctly consistent even when we thought it was tricky.
It does look tricky. Yeah, there's a product rule right there, which looks nasty. So negative 3x squared. And then here, the derivative would be 2y dy dx. That looks good. And then derivative of this will turn into a 1 y squared. Awesome. Then 3y squared dy dx. That looks great. Then negative 2xy negative y squared and 3. That looks great at this stage. Now we've got these two to contend with. That should go over there with the opposite sign, opposite sign. So dy dx comes out. So that should go to the denominator. Yeah, I think you folks have that. Got it.
Okay.
Oh,
Awesome.
yeah, ChatGPT, it just gives out weird answers. I found it.
It
doesn't do
sometimes
it
does,
doesn't
yeah.
do like differentiation so well.
That's weird.
Yeah.
What's weird about those AI tools is they actually started out really good, but they're getting worse as they get more and more results. The more they feed back on their own material, it's
Yeah.
degrading it.
Really?
Really weird.
ChatGPT trained on like internet scraping.
Yeah,
It's like,
but it's getting to the point where their own scraping is becoming their output as well. So it's kind of feeding into itself, degrading it. I think it's happening more with like image generation than maybe ChatGPT, but it's a problem for all of AI.
I did an internship
Really
with
weird.
AI.
Well, I can technically explain it. So the reason why AI struggles with that
Mhm.
is because so AI's right now is a very base form of others. ChatGPT's AI is so basic that giving it a complex math equation hurts itself because it can't possibly comprehend it in its full entirety. So it kind of makes up its thing as it goes.
Like the $44,000 computer at INL, like most AI is like 3-year-old and they're like, this is a 5-year-old.
Which is phenomenal, right?
$44 million for 2 years.
That's
AI
insane.
takes a long time to build up
It's
because
probably just a room full of servers or something.
So
Jeez.
the reason why AI takes so long to build up is because they're artificial intelligence. So they're basically, they start out as we start out.